thanks everyone for inviting me to the talk and for organizing things so smoothly. I'm very happy to be here, and hopefully I can provide at least a decent amount of value for any Scala learner and teacher. My talk is called What I Learned from Teaching Scala to 30,000 Engineers. So here's my screen, and this is what I'm about to talk. So as Sandra introduced me, my name is Daniel, and I am a software engineer. Right now, I'm an independent software engineer, and I teach Scala and a bunch of Scala-related tools, including Akka and Apache Spark and some libraries based on Scala at a website that is called RockTheJVM. So you can find all of my content and all of my materials and articles and videos at rockthejvm.com, and you can find me at RockTheJVM on all the socials, on YouTube, and basically everywhere on the web. And if you have any questions, or if you have something that I can personally help with, you can reach out to me at daniel@rockthejvm.com, and I'm more than happy to help anyone with any kind of experience. So if you're a completely newbie in the Scala world, I'm more than happy to help and provide support and learning materials and so on and so forth. So my talk today is about learning and teaching Scala, because in fact, we're all Scala learners to some extent. Scala is particularly complex on the JVM. I have a developer who works at Google, and he's particularly versed in Scala, and he compared somewhat unfairly Scala to C++ in the sense that Scala has so many features and so many ways of expressing things. Of course, the comparison is unfair. You cannot really compare a JVM language to a memory managed language, but still, he has a point that Scala has become pretty complex, and there's no shortage of new stuff to learn on Scala. And so we're all Scala learners in one way or another, and we're all Scala teachers, because as fans of the Scala language, we're either selling or teaching Scala to other people in more ways than we can imagine. If we are proper instructors, we teach Scala directly, and that's easy to acknowledge. But when we are, I don't know, maybe senior developers or team leads in our company, we are also teaching Scala to our fellow developers to probably set direction for the product that we want to develop, or for the library that we want to provide to other people, and so on and so forth. So we are also Scala teachers. So the goal of this talk is to impart some of the learnings that I've personally had in my 7 years, I think, of Scala teaching experience, and show some of the tips about learning and teaching Scala in a structured and methodical way. Because the end goal is to have more learners and more teachers in the Scala ecosystem. Scala is such a great language and such a great tool that it deserves more learners and more teachers, and I hope I'm gonna be able to provide some of those tips for you. So I'm gonna start about Scala being touted as a multi-paradigm language that can do basically everything. So Scala is marketed at everyone, but the primary target is the so-called established engineers, meaning people with some good familiarity with computer science fundamentals, 1 or 2 years at least of programming experience in the wild, and preferably with Java background, because Scala is based on the JVM. And of course, when you learn Scala, we also introduce some of the context related to the JVM, like garbage collection, thread management, and so on and so forth. Now, because Scala is primarily targeting established developers, there's a trade-off in what concerns the learning experience and the teaching experience for the particular level of experience that we're talking about. So the plus side of teaching and learning Scala as an experienced developer is that an experienced developer will always involve their current mental model in everything that they're learning. So for example, if you're teaching the object orientation of Scala as a programming language, people naturally bring in their current experience and their current mental model into the concept that they're learning. For example, the garbage collection, how memory is being allocated, how threads generally run, and so on and so forth. And this has a smoother learning curve when they're starting out. However, this experience will also involve a I like to say a healthy dose of skepticism, because people are generally reluctant to learn new things if it has some perhaps memory concerns or performance concerns. And one of the first examples that I illustrate in my videos and in my trainings and courses is a very trivial immutable data structure to the point of illustrating how immutable data structures work. And this is pretty simple, like a counter with an internal value with two methods that will return a new instance every time. And the very, very, very first thing that I almost always get is something like this. Hey, Daniel, isn't this allocating too much memory? Isn't this inefficient in a way? Isn't this going to cause problems in terms of memory consumption and in terms of performance? And this is good. This is the healthy kind of questions that I expect from experienced engineers. However, many engineers, being so experienced, I like to say that their mind is already made on certain topics. For example, if I show them this exact example that I showed you previously, they're going to trash Scala outright, saying that Scala is not good for anything because it's so inefficient, you waste memory and you waste time and so on and so forth, before I even get to make the point that you can still create high performance Scala code while still keeping the immutable data structures and the pure functional programming principles in place. And so these are some of the trade-offs that you will have to make while teaching Scala to experienced engineers, and this is the kind of context that you will need to take into account. Also, because experienced engineers are, I don't want to say stuck in their ways, because many developers are very flexible, but their mind has already been made on a couple concepts, and they have some trouble internalizing some new things that might conflict to that. Experienced engineers have a harder time unlearning things before they can learn new concepts. So for example, if I show them a list and I give them an exercise to process that list in any way, the first question that they get stuck on is, how do I loop through the list? And this is an example of a question that basically suggests that a new mental model is needed, and the replacement of that is going to be very hard. At the same time, when I show more complicated topics or something that detaches from the concept of a collection or of a data structure, for example, an asynchronous computation or the absence of a value, again, a similar kind of question is, Daniel, how do I extract that value so that I can process that in any way? And so this kind of prior mind setting for experienced engineers, this generally tends to create a bad habit and a steeper learning curve, or more resistance in what concerns learning some more complicated topics like monads, which is quite abstract, and probably thousands of blog posts and articles and videos have been, and a lot of ink has been spilled on this concept. Implicits and givens now in Scala 3 is probably going to break their mental patterns in what concerns making code available for unrelated types, and type relationships outside the hierarchical object-oriented model. For example, the notion of type classes is generally pretty hard to teach to classical object-oriented programmers with lots of experience. And in my experience, the more time people have spent in these classical mental models, the harder it is for them to internalize these new mental models. Variance is also quite difficult to teach because it involves substitution as a more abstract way of enforcing type relationships instead of the extends keyword in object orientation. And also asynchronous programming primitives as standard values, these are also quite hard to impart. And so what I want to send in this talk is a few tips on how to approach these kinds of challenges when you teach Scala to experienced engineers. However, I'm also going to talk about teaching Scala as a first language, because I've also had quite a bunch of students learning Scala as their first language. I generally tell people before enrolling in my material and in my courses that Scala is primarily targeting experienced engineers with some computer science fundamentals, but if they want to learn Scala as their first language, I'm not going to stop them. Quite on the contrary, I'm going to help them, and I'm going to provide as much support as I can possibly create. So one can learn Scala without any computer science background, and there are many positives here, and we should have more newbies in the Scala programming world. The first positive is that the functional programming mindset is counterintuitively much easier to teach on beginners than to existing experienced programmers. That is because there's nothing to unlearn. That is because there's nothing to resist. So they don't have an existing mental model that causes any friction with the functional programming mindset, with immutable values, with passing functions as arguments and returning them as results. Things of that sort are much easier to teach to beginners. Also, on the positive side, once we establish a general foundation of essential concepts, the higher level abstractions and the things that we generally deem to be harder in the Scala ecosystem, such as higher order functions and type classes and variants and implicits and things of that sort, these are also easier to teach to people starting with Scala without any computer science background. However, the negative side of that is the initial concepts are harder to teach. For example, it's hard for beginners with no computer science background to figure out, for example, how recursion works or how the computer actually crunches the numbers to get to the result that they desired. Also, asynchronous programming primitives are also quite hard to teach for beginners without computer science background, because they don't have any preconceived notion of how threads work or how the computer actually manages to crunch the numbers. So these initial concepts are harder to teach, and they have a steeper learning curve. But once that learning curve has been flattened, the harder concepts are then much easier to impart. So given that we have so many benefits to learning Scala without any computer science background, we should encourage having more newbies join the Scala ecosystem and joining Scala as their first language. And to do that, we as instructors and as teachers of Scala, we need to create some more compelling use cases for Scala as a language, because right now, Scala is used for these very abstract backends for things like cats and cats effect, or Zio, or asynchronous programming with Akka and reactive backends and stuff like that. And these are really hard to teach for newbies without a computer science background. We need to create some baby steps for them to join the Scala ecosystem, because right now, in the JVM world, Java is probably the uncontested champion here, because you can define so many applications that you can run on your laptop or on an Android phone, or things that you can actually physically touch and feel without spending a year or two building your thing. So I'm going to talk about learning Scala as a newbie, because I've seen some people learning Scala without any computer science background, and I saw some patterns, and I want to impart some tips on how to approach Scala as your first programming language if there happens to be a developer or a potential Scala developer with no CS background in this talk. So Scala and programming in general will be a simple extension to basic mathematics. For example, when you define a condition like if a condition, then you return a value, otherwise you return another value, that whole thing is an expression because it evaluates to a value. And the way that I like to talk about that is show the kind of mathematical definition where you have x equals, and then you open a large curly brace, and then you say 3 if some condition and 4 otherwise, or things along those lines. And so I noticed that people learning Scala without computer science background tend to come with a background of mathematics or other hard sciences like physics. And so it's easy for me to teach Scala in this way by creating analogies to pure mathematics or pure science of a different nature. Also, functions as a cornerstone of functional programming and of Scala programming in particular, functions are defined in terms of expressions. So the definition of a function is a single expression, and that expression can also include the definition of the function. So you can have recursive definitions, and people generally catch this as a concept. What they don't have, what they have more difficulty in is figuring out how those expressions are actually computed. And this is often the case when people start to learn Scala after they've gotten just a little bit of taste of Java or other programming languages like Python. So people getting into programming, for example, they learn like 3 weeks of Java or 2 weeks of Python or things of that sort. And then they look at a recursive function in Scala and they go like, but I was under the impression that the computer does things step by step. How is this recursion actually computed? Can you explain how Fibonacci of 1000 is actually computed, and so on and so on? And so although the function definition as a recursive expression actually makes sense to them, the actual evaluation of those expressions can actually pose problems. And so you need to be, as an instructor, if you are teaching Scala to newbies, you need to be careful to also explain how the recursions are actually computed step by step. Now, people with no computer science background learning Scala as an extension of basic mathematics also realize pretty quickly that expressions returning a unit are quite unnatural because they don't return any meaningful values, but they produce effects. For example, printing things to the console, or sending a packet of data, or printing or modifying something on the screen, and so on and so on. And so expressions returning unit are unnatural, so they naturally put the expressions returning unit in that kind of box. The same goes for exceptions, because when you throw an exception on the JVM, regardless in which language you write, either in Java or in Scala, an expression returning or throwing an exception also produces an effect without actually returning any meaningful value. So it's important to separate the notions of expressions evaluating to a meaningful value and expressions that do something rather than actually return any meaningful computations. Speaking of computations, it's easier for programmers or potential programmers with no other computer science background to think of computations as values. Anything is a value. 2 plus 3 is a value. The if expression that you see on screen is a value. The absence of a value is also a value. For example, an option. A failed computation is also a value. And so notice that we try to distance ourselves pretty naturally from expressions that return unit or that produce effects without returning any meaningful values. Also, asynchronous computations are also values, although they are quite harder to understand, quite harder to grasp how the process actually performs under the hood with thread management and so on and so forth. But the concept itself is pretty easy to grasp. Now, implicits and the harder concepts, like I mentioned earlier, they follow a smoother learning curve after the essential foundation has been laid. And so implicits will prove the existence of types, as someone with a background in mathematics will very easily accept. And variance implies substitution, in the sense that, for example, when you define a covariant data structure like a list, it's easy to imagine that a list of dogs is also a list of animals. So you can simply write list animal equals new list of dogs. And conversely, if you can imagine a realistic concept like a vet, which treats animals and treats your pet, a vet of pets is a proper substitute for a vet of dogs. So if you require a vet that can treat your dog and you bring in a vet that can treat any pet at all, they can treat your dog as well. So this is a good example of contravariance, and this is a good example for people to get a sense of what the variance concepts mean. Now, variance from a mathematical sense also implies inclusion in the set of possible values. So for example, the set that contains the list of all dogs is included in the set that contains all the lists of animals, because the list of dog is also a list of animals. At the same time, a list of cats is also included in the list of animals. So the covariance type is described by this mathematical inclusion sign. Conversely, the contravariance concept can also be described in terms of inclusion, in the sense that the vets of pets, that is, the vets that can treat every single pet, is included in the set of vets of dogs, because there are vets of dogs that cannot treat any other animals, and the same for any other kinds of animals as well. So I like to teach variance in terms of substitution and in terms of mathematical inclusion. And people with no computer science background usually get these kinds of concepts, obviously with various degrees of mathematical versatility or experience, let's say. So in very short, when you learn Scala as a beginner, just think that programming is an extension of basic mathematics. So our job as a programmer is to define a large expression, a giant expression that computes one thing that you like. So your job is to write that expression. And when you press the button, the computer's job is to actually run the numbers and return that value to you. So this is how I like to teach, that I like to impart the essential concepts of functional programming, and in Scala in particular, for people with no computer science background, but with some mathematical background. That has been my experience in the people that I've had in my courses learning Scala without any computer science. They had some background in some other kinds of hard science. Now, what about learning Scala for experienced engineers? The learning Scala for experienced engineers is more about internalizing the functional programming mindset and Scala as a new way of thinking and approaching code, more than just a better Java with a different syntax. So this is what I like to start with first. Scala is not just a better Java. So as an existing engineer, you shouldn't really expect a programming language to be more of the same. Although many programming languages just express more of the same, when you learn Scala from an imperative programming mindset, you should not expect Scala to just be a better Java, expecting imperative programming with a different syntax, but rather open your mind to completely new ways of thinking and approaching code. So the first thing that I like to teach is to think in terms of expressions instead of instructions. So expressions are structures that evaluate to a single value, whereas instructions are things that you tell the computer to do step by step. So let me give you some examples. I like to talk about if structures being expressions in the sense that they reduce to a value, and I'm not talking about the kind of code that you can write on the right-hand side of the screen, but I advise them not to write it because that enforces or that reinforces the existing imperative mindset that the engineers might currently have. At the same time, processing data structures and collections in particular will naturally bring about the idea of looping or of iterating through a collection or a data structure. And I try not to talk about that, but rather talk about the kind of expression that you can return, the kind of value that you can return by writing an expression. So we need to think in terms of expression, not instruction. And when you think in those terms, you naturally look for different kinds of solutions to the same problem. So for example, if I ask people to return a list where each element is modified by 1, they will not think about looping anymore, but they'll think about what kind of method or what kind of expression can I write on this list so that it returns modified. And so this idea of thinking in terms of expressions instead of instructions might sound really, really obvious when I talk about it now, but when people learn Scala with some existing programming experience, this idea is really foreign to them. And so it's a good idea for an instructor to enforce this idea upfront from the very beginning. Now, in terms of functional programming versus the object-oriented programming, there is a discussion. There's not just one discussion, but there are many, many discussions across the web of which paradigm is better. I like to talk about functional programming when I introduce this concept in terms of there is no discussion of which paradigm is better. There's no picking of functional programming or object orientation. You can have both, and you can have them very easily. Functions are just objects with apply methods. This is how Scala as a functional programming language can be implemented on top of the JVM. So for example, when you write something like this, when you write a lambda, this is the same as defining an object to implement one of the traits in the Scala standard library, and you instantiate those traits on the spot, and you provide the apply method, which the Scala compiler interprets a little bit differently. So when I talk about functions as objects with apply methods, this idea usually sticks with people coming from imperative backgrounds, and especially to engineers with object-oriented backgrounds. For comprehensions at the same time, they're not loops, they are expressions. And notice that the foundational idea that we think in terms of expressions, not instructions, will reflect back here. And now it's easier for people to understand that for comprehensions there are structures that evaluate to a value. And so there are expressions, not some looping structure that the computer does. Obviously, the bytecode will actually perform that under the hood, but that's not your job to think about. When you write something like this, you think in terms of expression and you let the computer run the numbers. So when you write something like this is the same as a chain of map and flat map and with filter chains. And I'm going to talk about those soon as well. So based on the idea that for comprehensions are expressions, allows you as a learner to detach yourself completely from the idea of looping itself. And so you can extend that concept of a for comprehension as a chain of map and flat map chains to other concepts as well. For example, to asynchronous computations, or the absence of values, or potentially failed computations, or any other kinds of monads or other data structures. Speaking of which, if you want to learn abstractions such as monads or other type classes, these are much, much easier to grasp now that you've laid this foundation. So it's really important to sequence these foundational ideas step by step. Instructions, not expressions, and then for comprehensions as expressions, not instructions, then for comprehensions as something that can reduce to a value, there's not iteration there, and then detach yourself from the notion of iteration completely, and then just apply the notion of comprehensions to other concepts as well. Now for the harder stuff, asynchronous computations are also expressions, so you need to treat them as such in the sense that you can also apply functionals like map and flat map and other kinds of methods on asynchronous computations without actually caring about when those computations will actually end. Variance is another very hard topic, and this is quite hard to teach to experienced engineers because they're used to this object-oriented hierarchy. And so I talk to people about variance in terms of substitution as well by using the exact same example. A list of dogs is also a list of animals, and so you can have the proper substitution in the sense of covariance, and a vet of pets is a proper substitute for a vet of dogs because a vet of any pet can treat your dog as well. Now, a real punchline that I like to impart to people when I teach Scala foundations is how to pick variants for your types, because people are asking me, okay, variance is really nice, but how should I choose whether a data structure or a type should be covariant or contravariant? And if you want to take something from this talk as a Scala learner, it's this. This is a pretty short punchline that saved me a year of experience, or lack thereof, programming against covariant and contravariant data structures. So if it contains T, or if it produces a value, then you should make it covariant. If it consumes a value, you should make it contravariant. Other notions like type classes and relationships between types are much easier to learn after that, because you can distance yourself from the object-oriented inheritance model as the only way to do things. I have some more examples here, but what I advise teachers of Scala not to say when teaching Scala to experienced engineers, to not start with variables, because when the vast majority of Scala tutorials and Scala courses that I see on the web, they start with here's the value and here's a variable, because the instructors probably imagine that this is something that people can resonate with. I advise against that, because the notion of a variable is pretty well understood, but it's pretty dangerous because it reinforces the imperative mindset that we want to move away from. And looping is another one of those concepts that I really never talk in my live training. So this is something that I've learned in my previous year of holding trainings at companies. And this has been very, very effective in that people can very easily think in terms of expressions later, because now they don't really have any tools to iterate through a collection, for example. And so they naturally think in terms of expressions like map and flat map and things of that sort. But I later tell them about variables and loops after they're already comfortable with functional programming primitives and the functional programming mindset, because at that point, they're not even concerned about solving their problems in terms of variables and mutable data structures and loops, because they already have the tools, and they can only use these tools when needed in terms of performance and critical performance of that. I also talk to them about how you can make really fast Scala libraries and applications using pure functional programming. Now, the final thing that I want to talk about is what to talk about when you're showing or when you're showcasing a library or a tool that you've worked on, because we want to teach people basically everything that the library can do. But what I advise people to teach Scala libraries with is to something very simple and tangible that people can actually touch and feel by writing very, very little code. So with baby steps, you can get to a tangible result very quickly, and this is how people get incentivized to start. Avoid the real life scenarios right off the bat. Present the real life scenarios after people have had enough of experience with your tool. And focus on the main way to do things. This is what that abbreviation means. Focus on one thing that your library does and teach that well, so that people can master a core element or a core concept, and then they can expand on that. Try not to show everything that the library can do, because as Scala programmers, I know how excited we are when a tool that we've written is so extensible and so easy to compose and so versatile and can show can basically program the world basically with your libraries. I try to avoid that, because that can cause confusions. And people also ask for the best practice. When you have like a million ways to do things, what's the best practice? So try to show people, hey, here's the practice that I follow. Here's what I think the best practice is. And once people have enough experience, give alternatives. So Scala is an amazing language. It needs more learners and teachers. And I hope that through this talk, you've gotten some ideas on how to become a better Scala learner and teacher. I'm Daniel. You can find me at RockTheJVM.com and at RockTheJVM on Twitter and LinkedIn and YouTube and basically everywhere on the web. I'm available for any questions. So thank you for attending my talk.